We are covering the Reynolds number and the Moody diagram for the FE Civil Exam, a core concept in the Fluid Mechanics section of the NCEES FE Reference Handbook. The first step in any internal pipe flow problem is to calculate the Reynolds number, which determines the flow regime. The formula is RE equals velocity times pipe diameter divided by the kinematic viscosity. Remember, kinematic viscosity already has the fluid's density factored in, which is a common shortcut provided on the exam. Let's walk through a typical problem. Imagine water at 60 degrees Fahrenheit is flowing at 5 feet per second through a 6-inch diameter commercial steel pipe. From the handbook's tables, the kinematic viscosity of water at this temperature is approximately 1.21 times 10 to the negative fifth feet squared per second. A major exam trap is unit consistency. The diameter is given in inches, so we must convert it to 0.5 feet. The Reynolds number is then calculated as 5 feet per second times 0.5 feet, divided by 1.21 times 10 to the negative fifth, which results in a Reynolds number of approximately 206,600. This value is critical because it tells us if the flow is laminar, transitional, or turbulent. Flow is generally considered laminar for a Reynolds number less than 2,100 and fully turbulent for a Reynolds number greater than 10,000. Our calculated value of over 200,000 is deep in the turbulent zone. The FE exam will almost always give you problems that fall clearly into the laminar or turbulent categories to avoid the ambiguity of the transitional zone. Now we need to find the friction factor F for laminar flow. The equation is simple. F equals 64 divided by the Reynolds number. But for turbulent flow, we must turn to the Moody diagram, also in the Fluid Mechanics section of the handbook. Using the Moody diagram requires two inputs: the Reynolds number on the horizontal axis and the relative roughness on the right vertical axis. Relative roughness is the absolute pipe roughness, epsilon, divided by the pipe diameter, d. The handbook or problem statement will provide roughness values for different materials. For commercial steel, a typical absolute roughness is 0.00015 feet. The relative roughness is 0.00015 feet divided by our 0.5 foot diameter, which equals 0.0003. Now, on the Moody diagram, locate a Reynolds number of roughly 2.1 times 10 to the fifth on the logarithmic x-axis. Follow that line up to the curve representing a relative roughness of 0.0003. From that intersection, move horizontally to the left axis to read the Darcy friction factor, which will be approximately 0.0175. Be careful with the logarithmic scales. Misreading the chart is a frequent error. The final step is to calculate the head loss using the Darcy-Weisbach equation. Head loss, HF, equals the friction factor F times the ratio of pipe length to diameter, all multiplied by the velocity head, which is v squared over 2g. If our pipe is 500 feet long, the head loss is 0.0175 times 500 feet over 0.5 feet, times 5 feet per second squared over 2 times 32.2 feet per second squared. This gives a head loss of about 6.8 feet. A good mnemonic to remember the entire process is ride the Moody freeway. First, calculate R for the Reynolds number to find your ride. Use this to determine if the flow is T for turbulent, which tells you to use the Moody diagram. Finally, find the F for friction factor and plug it into the Darcy-Weisbach freeway to find the head loss. For free practice questions, AI-powered explanations, and more exam prep tools, visit openexamprep.com. That's openexamprep, all one word, .com.